think we'll get going now. So yeah, I'll just introduce myself again. James Latham, Head of Enterprise Sales, and joined today with my colleague Eddie. We're going to do this Creo Simulate Elite webinar. So Eddie's in one of our technical team. He's been with us a few years, but prior to that, actually was working as a design engineer, and he's had good experience using simulation in the design environment and upfront to validate and verify what he's been doing. You can also see there's a download link there. I think it's been posted in the chat. There is a CAD file there for that you can download that Eddie's going to be working through, so you can review it and have a go yourself. On the next slide. So very quickly, the goal of today is some outcomes is really for you to try and understand why we as well think simulation is important, to go through some of the tools that are available to you in the Creo Simulate solutions that you have, and the Creo Simulate Elite is included in the Creo Subscription, and then there's going to be the bulk of it is a walkthrough and of how we would go around performing a structural analysis in this tool set. On the next slide. So very outline of the agenda really. I'm just going to do a very quick introduction about PDSVISION, because we are sort of a newish company joined together with started again in July when Wild Analysis, who I used to work for, are part of the big group now. And then I'll hand over to Eddie, who will go through the other points on the agenda, and then we'll wrap up at the end with Q&A. So you can put questions in the chat, and we'll aim to have a pick up at those at the end, but we can also take those offline and answer in more detail, email or through other contact. Okay, next one. So yeah, as I said, PDSVISION, based in Stockholm. They bought some companies in the UK a couple of 3 years ago, and we have now all joined together as one company called PDSVISION UK. Offices are based in Cambridge and Manchester. And we're a very big global organization. We share resource, and we've got engineers dotted around doing all sorts of CAD, PLM, and simulation tools. While the Wild team dotted as well. Some of them are in the US, some of them are in Central Europe also. And we've got access to a lot of skills and a lot of the engineers doing both services. They're also doing technical support, pre-sales, and they're also training and mentoring. So they're embedded in using this technology every day. Okay, next one. And really, PDSVISION now is setting itself up as a business that's involved in digital transformation, or this big digital thread. So this gives you a nice visual of the sort of areas that we're involved in. And today our key focus is on that digital simulation, the one that's highlighted there, and that's part of our many solution sets that are available. And then next one, and then just on this one really, another one of my big roles is to manage and grow and sell our ANSYS tool set for some very, very high level simulation capabilities. But there's a real link between PTC and ANSYS, hence why I think we were acquired by PDSVISION. And so there's a great sort of workflow about how you can move from PTC up into ANSYS as you get more and more comfortable and confident in using tools, simulation tools to really give you those critical insights into your designs, into your processes, how to innovate faster, and the magic time to market that we always hear about. But I think when you're doing things in a digital engineering environment, you are generally driving the development a lot quicker than you would do traditional ways of testing, physically testing, making, etc. So I'll hand you over to Eddie now. He's going to do the bulk of it, and then I'll be back on at the end. So thank you very much.
Okay, good afternoon, everyone. It's Adigbe Ubido here. So just a bit more about me before we get into this section of the webinar. So here at PDSVISION, I mainly focus on static and transient and structural analysis. And as James mentioned, I've got some previous mechanical design experience where I've used the upfront simulation to perform structural analysis in the design process. Okay, so first of all, we're going to go through what is the importance of doing stress analysis up front? And stress analysis allows you to assess the structural stability of your design to assess whether it's suitable for its purpose. And this allows you to kind of highlight the particular areas of weakness and give you information on improvements that you could make to make your design like an acceptable level of safety. So from this, you can reduce the risk of failure and remove the need for a lot of long-winded physical testing, which can take a long time and can be quite costly as well. So you end up with reduced lead times and costs. Okay, so simulation is included with all Creo Parametric products to some extent, with Creo Simulate it being the base level for this. And it allows you to perform structural analysis, and it's included with all Creo Parametric licenses. And the tools involved are quite intuitive, and you can generate some accurate results that give some information on the structural performance of your design. And if you're quite well versed with Creo Parametric, the user interface is quite straightforward and will be familiar. And using the software, you can apply design loads that you expect your design to come across during its service life, and this will allow you to see the design through from the design stage through to the simulate stage, where you can get some information on what improvements to make. And then you can move forward with the optimized part, where you can rerun the analysis to ensure an acceptable level of safety, and your design can be therefore optimized. And this is all within the same user interface, which makes it quite handy instead of moving from software to software. So here we have the follow along demonstration. So if you'd like to follow along, yeah, please download the step file that you can access through the chat window, and load it into Creo Parametric, and then you'll be ready to begin the demonstration. But generally, this is a pipe network that I've designed, and we're going to focus on the red and blue portions of it, which is a pipe with a nozzle, and it's got a blind flange on top. It's supported above by an I-beam by these lugs on either side, and it's subjected to an internal pressure of 1 megapascals, and it has a design temperature of 40 degrees Celsius. And the temperature loads is quite small, but it's just for illustrative purposes in this case. The material we're going to use is steel, which has a Young's modulus generally of about 200 gigapascals. And it's a linear elastic material, meaning that the stress is directly proportional to the strain up until the point of failure. And we're going to use an allowable stress of 130 megapascals. So what we're going to do is we're going to assess the deformations to assess whether the design is behaving the way we think it would with the loads that are applied. And then we're going to have a look at the stress distribution to gauge the level of safety of the design, and compare it with our allowable stress to assess the level of safety. Okay, so if you manage to open the model, okay, if there's any questions at the end, just put them in the questions window, and we'll get to them at the end of the webinar. But I'll just load this video up now, and I'll let the demonstration play through. Here's our model. We can see our pipe work with our lugs that are attached. Here's our model. Here's our model. We can see our pipe work with our lugs that are attached, and we can see our blind flange, which is attached to the top. So to enter into Creo Simulate, we go to Applications and Simulate, which is under this simulation group of icons. And this is the Creo Simulate user interface. Okay. So on the left-hand side, this is the Home tab where we've got most of our tools. We've got structure mode and thermal mode. Thermal mode is only included with some higher license types. So within Creo Simulate, we're limited to linear structural analysis. So we can go to our model setup, and we can see we've got a few different things. We've got Simulate Lite, which is a trial version, and we've got FEM mode, which allows you to export a model to ANSYS or Nastran. But this again is included with some higher license types. Here we've got the default interface, and this is essentially the default interactions that are going to be occurring between our parts. So say if we had a large model, we might want to sort of bond everything, and bonded essentially means that the two parts are fully connected, as if they've been welded. So this means that it transmits all loads between the surfaces. So here on our flange, this would mean that these were essentially binded together, and all loads are transmitted. We've also got free, which is the opposite of bonded. It means the two parts are essentially free of each other, and no loads are transmitted, and they're free to pass through one another. Contact is a non-linear behavior, and therefore it's only included with some higher license types. So we'll stick to bonded, and we'll click OK. Okay, so first of all, we want to apply materials to both of our parts. And now the main part of this body is structural steel. But this blind flange, we're going to apply a material given to us by Creo just to illustrate the different ways of assigning materials. So to add a material to our model, we go to materials, which is in our home tab. We can open this up, and under legacy materials, we can see all of the isotropic materials we have available to us. And for this one, we can sort of flick through and see what different properties different materials have. But for that blind flange, I want to assign this steel grade here. And you can see that the different material properties down here. And then we can click OK. Okay, so next we want to add our material. And to add a new material, we click this icon here when we're in our materials window. We'll give this a name, so we'll call this steel. We'll give it a typical value of density for a steel, 8,000 kilograms per meters cubed. We'll give it a Poisson's ratio of 0.3, which again is typical for steels. We'll give it a Young's modulus that we saw in our graphic earlier of 200 gigapascals, and we'll give it a coefficient of thermal expansion of 1.2 e to the minus 5, which again is typical for steels. There's material limits we can also add to this. If we wanted to define our material limits, we can add a failure criteria, and we can also add some fatigue data as well. So once we click Save to our model, that adds this material to our model window here, and we can click OK. So to assign these materials, we go to Material Assignment, and we'll see that our materials has been added here. So we'll add this to our main pipework, and what I'll just do is re-add this this steel grade here, Fe40. If you double click it, it should add it to this materials window here, and we'll click OK. And we'll assign this to the blind flange. Okay, so both of our parts now have a tag on it, and that essentially means a material has been assigned. Okay, so now we've got our materials assigned to our model. We now want to define our constraint. And our constraints are all located here in the Home tab. And what constraints essentially do is they stop movement in space of our model. So if you can imagine how our model is connected to the ground, we'll add different constraints to sort of represent that. So the different things that are preventing movement in our model in reality. One is the lugs on either side, and then we also have these flanges here that are connected to adjacent flanges of pipework. Okay, so first of all, starting with these lugs, what we're going to use is a pin constraint. And what a pin constraint does is it allows you to constrain a curved surface. And what it does is it constrains this surface in the radial direction. So if we apply it to this surface, you can imagine we've just put a joint through this hole here. And there's other constraints that we can apply to it as well. So we can constrain the tangential rotation, and we can also constrain the axial translation as well. So for this, we're going to constrain the tangential rotation. Okay, so now we're going to apply a similar constraint to the other lug, but this time we're going to allow the tangential rotation because it's already constrained in this model. So essentially, what you need to think about is the different movement that you're trying to prevent. So at the moment, this model cannot move in the Y and Z direction because that's the normal direction to this pin joint that we've applied. It can't rotate about the x-axis, but it can move in the x-axis because that's not being prevented because we've allowed that that axial movement in these joints. So that's going to be prevented by these adjacent flanges. So what we're going to do here is we're going to apply a pin constraint, a planar constraint to both of these flanges. And what a planar constraint does is it prevents movements out of plane. So in the normal direction to this flange, it'll prevent the movement, but it'll allow in plane movement. So it'll allow movement in the Z and Y direction, which essentially will allow the pipework to expand without over constraining the model. Okay, so we'll just give these labels. Call this one pin constraint. Call this one pin constraint 2. And we'll call this one planar constraint. Okay, so now we've restrained our model within space. We now need to apply our loads that our model is going to be experiencing. So first of all, we're going to apply our internal pressure. So as we're selecting these internal surfaces where our internal pressure will be applied, we might think that it's slightly difficult to see this undersurface of this blind flange. So to allow us to see this a bit better, we can explode the view, and to begin with, these parts are going to be at rest. So if we go to Manage View and we edit the position of this exploded view, we can select this item here, and we can just pull this away from the rest of the assembly. Okay, so that allows us now to edit this edit this face essentially. So we can now apply our load to the underface of this pipework. Okay, but what you might notice is that some of this face will be covered by this flange interface here. So the internal pressure won't actually reach the whole of this face. So there's a specific proportion of the face that we want to apply our load to. So to define our new surface, we can go to the divide surface tool, which is in our refine model tab. Okay, and we'll select our blind flange. We'll click OK, and we'll now draw on this face with our pattern that we want to apply our load to. So we'll start from the center of the blind flange, and we'll just draw a circle for now, and we'll dimension it so it's equal to the internal diameter of our nozzle. So I've applied 0.2 meters. Press enter, press OK, press this green tick mark. Then if I was to go back to exploded view, we now have a selectable face on the bottom surface of our blind flange, which will allow us to apply our pressure. Okay, so we'll go back to our home tab, we'll click pressure, and we'll select all the internal faces that we want to apply our pressure to. And we'll give this a value of 1 megapascals. We'll click OK, and that applies our load to our model. Okay, so as well as this, we can apply our gravity. So we want to know whether these lugs are sufficient enough to support the weight of this pipework. So we're going to apply gravity to the model. So using this this icon here, we can open a gravity load. We'll give this a name. And applying a gravity load or an accelerational load allows you to apply it in components, a vector with a magnitude, or the direction between 2 points and a magnitude. Okay, and it allows you to apply a specific set of units. But the units I want to use is in terms of gravity. And when you apply something in terms of gravity, you can, so essentially we want to apply it in the negative y direction. So I give it a value of -1. And when I click OK, we can see that it displays the direction of the gravity here, of the gravity load, in terms of one unit of gravity. Okay, so we can be happy that that's applied in the right direction. And finally, we want to apply our temperature load. So our temperature load is here on the loads. We'll give this a name of temperature. We'll select both of our components. It'll be uniform, but you can apply it in the sense of a function of coordinates or an external field if you wanted to apply that. So we'll change this to degrees. We'll give this a value of 40. And the value in our temperature load is essentially what temperature we want to run our analysis at. And the reference temperature is your design at rest. So when you were designing your model, what temperature is the model at essentially? So we'll give that a room temperature of 22 degrees Celsius, and we'll click OK. Okay, so we've got our loads that are applied to our model. So other loads that you can apply is a force or a moment. You can apply a bearing force which approximates the pressure distribution due to a bearing surface contact. We've got a centrifugal load which allows you to apply a load due to rigid body rotation. And we've got preload for bolts as well. Okay, so now we've applied our loads, we've applied our constraints. We've constrained this steel pipework, but this blind flange is also constrained because of the interface that we've defined. We've defined this as bonded, so all the loads are transmitted. And now we can set up our analysis and studies. But before you run an analysis or a study, you might want to sort of have a look at some of the ways we can simplify our model. So if you are running quite a large design, you might want to look at some idealizations, which essentially allow you to simplify specific parts into beams, springs, masses, or in this instance shells, because we've got a small through thickness. We've got connections, so we can apply a specific interface. So if we wanted two parts to interact differently to the global definition that we've applied as bonded, we can apply a specific definition between two parts as well. We've got computational welds. We've got rigid link, which essentially essentially connects two faces or reference points within space, which are separated by a distance. We've got a weighted link, which is similar to a rigid link, but it allows deformation. We've got a fastener tool, which essentially allows you to make a computational representation of a fastener. And as well as divide surface, we've also got volume region, which allows you to define a specific property or a load to a specific volume instead of a surface. We've got datum, so these can be used to create reference points or coordinate systems. We've got editing, which essentially allows you to edit your features within the simulation workspace without feeding that information back to parametric. So your edits will be independent of your parametric design. And we've also got our mesh tools using the AutoGem panel here. And this allows you to preview your mesh, or it allows you to apply specific mesh controls if you were interested in the sort of analytical side or improving the efficiency of your solve. Okay, so as well as that, we have measures just before we run our analysis, and this allows us to output specific quantitative data if that's what we were interested in. For example, reaction loads, reaction forces rather, and things along those lines. Okay, so we'll open our analysis and studies window. We'll create a new static model. And what we might see is we've got a constraint set that's defined in this top window, and we've got a load set that's defined in this bottom window here. And essentially, this is combining all of our constraints and loads into a specific set to be applied together. But we might want to apply our loads and constraints separately. So we're just going to show you how to do that, if that's what you please. So down on this bottom left-hand corner, we have our simulation tree, and this is independent of the Creo Parametric tree that we see above, and it's separated by this simulation green line here. So everything below the green line is involved with the simulation, and everything above it is fed through from Creo Parametric. Okay, so to create a new load set, so for example, if we wanted to see what our gravity does independent of the other loads, we can go to edit and we can create a new load set by going to new. Call this one gravity. We'll click OK. OK again. And if we look in the bottom left-hand side, we can see that it's added a new load set for our gravity. So now, if we go to analyses and studies, we go to new static, we can see that that we now have two different load sets that we can apply. So we can apply these by ticking them, and we can sum the loads, which, because we've got a linear static analysis, some of the loads will give us the resultant stress distribution, or we can just apply them separately. So firstly, we're going to apply gravity by itself. Click OK. We'll just call this one gravity. We'll click OK. Then we'll create a new static analysis, and this time we'll select both load sets and we'll sum them so we can get the resultant stress distribution from all our loads combined. And we'll click OK. Okay, so we'll just call this one combined so we can be clear. Okay, so on the file, we can see that there's some more advanced analysis types, but within Creo Simulate Elite, we can use a linear static analysis only, which restricts us to this setup here. Okay, so we'll run our first load case first, which is gravity by itself. We'll click this green flag, which begins our analysis. We'll click OK. Okay, again. And while this is running, we can open this display study status window. And this run status essentially prints off all the important information about our solve. So we can see our PC setup, or our analysis settings. We can see our units. We can see how many elements were used. We'll also see the information on each pass. And what each pass is essentially the model will be set up, and it will run through 3 times. Each time it will improve accuracy in areas of high stress gradients to improve the accuracy of the results. And on the 3rd pass, that's when you get your results. We'll see all our measures that are printed out. And again, if you were to define a measure manually, it will appear here. And we'll get all of our warning errors that will appear here in the console window. And also it will appear in the simulation diagnostics here. So the simulation diagnostics will give you all the information of what's wrong with your model. And if you get a warning which is yellow, it's usually okay. If there's something specifically wrong with your analysis, you might want to check some of the warning messages. But if it was to get run into an issue where it couldn't solve the model, you'd get an error, and that would show as red. But our run is completed, so we'll be able to view our results. So next, we'll just run our combined load case. Just open our run status window, just so we can see, we can track the progress. Okay, so our run is completed in 12 seconds, well, closer to 13 seconds. So now we've got 2 different load cases. We've got our combined load case and we've got gravity only. So first of all, we'll start off with gravity, and we'll just make sure that that gravitational load is doing what we expect. So to view our results, we can click this icon, and this will open this results window here. And our display types, we can display as a fringe, which essentially displays our quantitative data in the form of a contour on the surface of the parts. We've got vectors, which shows directional information. For example, if we wanted to know whether our stress was tensile and compressive, we can export. So we can create some graphical data, and we can also display things on the model as well. For example, loads applied, or our mesh, if we wanted to view our mesh. Okay, so we'll stick with a fringe, and for our quantity, we'll click displacement. We'll change our units to millimeters, and we'll also deform our model with a factor of 10 scaling, and this will essentially exaggerate the deformations that the model sees, just so we can get an idea of whether it's behaving as we thought it would. So we go to OK and show, and we can see how our model deforms. Okay, so this is how it deforms under the load of the gravity. So the gravity is acting in the negative y direction, so it's pulling down on the model. So where it's red, it's got the higher displacement, and we can see that where it's restrained at these 2 lugs in the y direction, we've got quite a small displacement, and that's because there is a zero deformation that's defined on these surfaces. Which is why we have such a low deformation in these locations. Okay, so we can look at that and be sure that our gravity is defined in the right direction, and it's behaving as we thought it would. Okay, so we can close this window now, and we can see what effect our loads have on the combined load case. So we'll review our results. Firstly, we'll look again at deformation, and we'll change this to millimeters. And within our display options, we'll deform our model again, but this time we'll animate our model. and we can choose how many frames we want to animate it for. And essentially, this will animate our model from rest to our final load that's applied. So we can click OK and show. And this is essentially how our model is behaving when we apply all our loads to it. Okay, so we have this expansion due to internal pressure. We have gravity, which is somewhat playing a part in the deformation, and we have our temperature, which is causing thermal expansion as well. Okay, so we have our legend along the right hand side, and that essentially prints off, shows us the values in which the colors that we can see. So our maximum is at the top here, which is 0.7479, and we can change this legend to something that will print off a bit more numbers which are a bit easier to understand. So we'll get rid of some of those significant figures, and we'll distribute these levels linearly from first to last. Change this bottom one to 0.015, and we can also edit from this window here, where we can get rid of some of those levels. So we can change the maximum and minimum from this edit legend window, and we can change how many levels that are involved. And we can click OK, and our model will readjust. Okay, so later on I want to view some of these results side by side. So what I'm going to do is I'm going to save this plot, and I'm going to save it as deformation here on my desktop. Okay, now that's saved, I can close this window. And next, I want to look at the stress distribution around this model. So I'll leave it as stress when I create a new results window. We'll change our units to megapascals, and we'll leave this as undeformed for now. So we can just see the stress values that are distributed throughout. Okay, so this is the stress that's developed from the deformations that occurred earlier. Okay, so we can see we've got quite a hot spot in this area, and also on the area that's directly opposite as well. One way we can look at this a bit closer is if we use a capping or a cutting surface. Okay, so I can go to new to create a new capping or cutting surface. I want it to be 50% depth, which is halfway through, and I want it to be in the YZ direction. So I'll click that there, and I'll hit apply just to see what that does. And that just shows me the stress distribution on that mid plane that we've defined. But what a capping surface does is it also shows the rest of the model behind the surface that we've defined. So as well as this surface here, we can also see the rest of the model behind it. Okay, so this is the model that I want to view. I can change these values here. So we had an allowable stress of 130 megapascals. So I'll change the top end of this legend to 130, and I'll change the bottom to 10. And now what this does is anything that is displayed in red essentially is above our allowable stress. So we might want to sort of add some kind of improvements to this area, whether that's to add thickness to our design or to add some kind of radius to sort of reduce that discontinuity. Okay, so now we've created our stress plot. We'll go to save that as stress. And finally, I want to get some more quantitative data of the stress across this line here. Okay, so what I'll do is now is I'll create another set of results. But this time, instead of fringe, I'll create a graph, and I'll change this to megapascals. And I want to define this on the arc that we seen earlier. So you can have your horizontal axis as relative to the curve arc length, or any coordinate as well if you wanted to define it in that direction. So to select my graph location, I'll click that cursor icon, and then I'll click this edge here where we saw that region of high stress. We'll click OK, and we'll go to OK and show. And this shows us some quantitative data of how our stress is distributed along that edge. And what I can do now is I can display all of my results in the same window by going to this open icon here, going to my desktop where I save my plots, and I can open them one by one to view them side by side. So this tells a bit of a story of how the structural analysis has gone, and how my design will perform under the applied loads. So essentially, all the loads combined will cause it to expand in this region, which will cause a compressive region on this inner side. That results in a high stress region, which I can see visually using this plot, and that exceeds our allowable stress. And on the left-hand side, I can also view some quantitative data of what specific region exceeds that maximum stress here. Okay, so that was our demonstration. It was just an example I thought illustrated how to apply different load types, and the flexibility of Creo Simulate when performing structural analysis. Okay, so there's a few options that you can choose when it comes to upfront simulation, depending on what you require. So first of all, we've got Creo Simulate Elite as shown in the demonstration. But if you require some additional analysis tools, there's options like Creo Simulate Extensions, which gives you access to more advanced capabilities within Creo Simulate, like non-linearities and dynamic analysis. And if you'd like to perform CFD, then you could look into Creo Flow Analysis. There's Creo Simulate Live, which gives live feedback on the performance of your design while you're in the designing process. And that's powered by ANSYS. So for example, in our demonstration, if we were to add some kind of fillet in that region where we saw that high stress, it'd automatically refresh and display the resultant stress distribution, and sort of give us feedback on whether that like solve the problem. Then we have Creo ANSYS, which uses the mechanical solver within ANSYS to perform structural thermal and modal analysis. And we've got webinars on the bottom two options in the following weeks. And if you've got any questions about any of these, then yeah, feel free to reach out to us, and we can provide more information on that. So over to you, James.
Yeah. So yeah, just wanted to share that we've got another one next week will be delivered by my colleague Alex Jones on Creo Simulate Live. As Eddie said, there's another tool set that works in a live environment. Very good feedback when you're making changes to your designs. And then the following week, my colleague Mohammed will be doing a presentation on Creo ANSYS Simulation and Simulation Advanced, where there's a real good link between using an ANSYS solver within the Creo platform. We've also got an event on the 28th of November at the MTC in Coventry, and it's the link's there, PDS forum. We'll send it out to everybody as well. It's a one-day event. There'll be some presentations both from PTC and ANSYS, and also some of our engineers will be there doing workshops and various aspects on the toolkits that we have in that digital path and flow that we showed earlier. So it'd be great if some of you can sign up and join us on the day. Both, I think Alex, Eddie, and Mohammed all plan to be there. So there's a session that those guys are running on what we're covering in the webinars as well, and you can ask questions of them and sort of pick their brains as engineers doing this every day. So just on to the last one, really. I just we've got some questions. We've got one question. Obviously, we will make this available, the recording. I think it'll take a few days, but we'll get it sorted out so you can then rewatch it and work through. I know there were some issues with the chat box, so I'm very sorry. Hopefully you've got the link, but we can also sort out that. We've had a question, Eddie, about using it for welds. Is that something that you would do with this, or would you use another tool set that we have?
So the weld tool within Creo Simulate is for defining the connectivity between shells. So for sheet metal parts, you can use it to connect them via perimeter welds, end welds, or spot welds. But it's more for load transmission between parts rather than taking into account things like imperfections and residual stress. Welds for solid parts need to be defined in Creo Parametric using the weld wizard or prior to entering into Creo Simulate. Okay, so we've got another one here. How do I get access to these simulation capabilities? And all Creo Basic subscription licenses have access to Simulation Elite for structural analysis, and it's completely free. So if you're an existing Creo user, then you should already see the simulation tab in your Creo interface. But if not, contact us, because there's some older license types which might need upgrading before you do that. But beyond what we've shown today, you'll need an additional license, and we can arrange a demo or a trial license accordingly. Okay, so we've got another one. Will Creo Simulate do any CFD flow analysis? And the answer to that is no. You'll either need to use Creo Simulation Live, which is featured in our next webinar. Creo flow analysis, or you'd need to look into using ANSYS Fluent. Okay, so our final question is, will Creo Simulate have all the tools required for validating a design? And this depends on what loading and materials your product is likely to face. For example, for metallic structures on the basic loading, it might be sufficient. But if you've got more complex materials like rubber or dynamic loading such as vibration, you'll need further capabilities within Creo Simulation extensions or using ANSYS for final validation. But here at PDS, we're a full ANSYS channel partner, so we can support you with any ANSYS software and training if that's what you need. And this is for when Creo Simulation or Creo ANSYS simulation tools aren't suitable. Alternatively to this, we can offer FEA stress analysis consulting services, and this you can use this to kind of check your final designs after you've initially done some Creo Simulate in early stages of the design process. But yeah, that's the end of the questions we have in the questions pane. But I'd like to thank you all for joining. And if you've got any further questions, please reach out via my email address that you see on the screen here. Okay, thank you very much, and goodbye.